Oh, good morning, good afternoon, everybody. So today I'll be going over my submission for the CSCE 2023 presentation in Las Vegas, Nevada. This is my work related to graph-oriented modeling of process event activity for the detection of malware. So I'm Kenneth Brzezinski, the corresponding author. So just as a quick overview of malware, according to Microsoft Threat Report, 70% of all new malware threats are zero-day attacks. And what that means is zero-day attacks are attacks which have no known signature known to the security community. Therefore, they're of malware and pieces of software they're of particular concern. And it's such that malware has become more sophisticated with how it works through a mechanism called metamorphism. What metamorphism is that a malware can actually take itself, mutate it, encrypt itself, and then package itself all back up. So this image here in the top right just shows exactly how this can be done, where a virus body actually can decrypt itself, mutate itself, and then pack itself all up. And compared to simple static techniques, where we were able to look at, for example, certain strings of malware within the malware, when we used to be able to search for these common substrings and then come up with a signature. But the thing is, these simple static techniques are no longer viable, mostly because malware is, of course, doing this using these mechanisms where it can mutate itself, but also because it's also changing how it looks in each iteration. Therefore, the signatures that were created before are no longer useful. So as an overview of malware and its execution, one thing to note is that malware behavior is very dynamic and it spans time and space. So it's not just it doing one thing, it's sort of a pattern of behavior where you have from the initial execution to trying to gain, and then you're trying to gain persistence, you're creating files, deleting files, making changes to the registry, all this. So the whole point is that it spans time and that it has a temporal space. And it spans space in the topological sense, which is to say that malware also has sort of a chain of how it's executed from its parent process to its daughter process. So there's a chain there, and we can see on the right here this figure where these red nodes correspond to the cryptic.exe malware and sort of the processes that it spawns based off of itself, while the green nodes are benign processes that are associated with the Windows operating system. So one thing to notice that nodes in this figure represent processes, and these edges reflect the parent identifiers and the process identifier and the parent process identifier relationship. So that's how you can sort of move along the chain and find out which process spawns from which one. And of course, each process has to do something on the operating system itself for it to be logged in a way, and that's through event activity. So whether it's doing something on the registry, doing something in the file system, it's using network sockets in order to make connections, or it's opening threads. At least with our implementation, each process is responsible for one or more event activity, and those are the things we're trying to log. It's logged based on its dynamic execution. So with these research, so going straight into research objectives, based a little bit on what we've spoken about, the question is, what features should we consider if we want to characterize malware better? Additionally, how do we want to model the malware execution topology? So there's a lot of information. We don't want to consider the processes in isolation. We want to consider over that time series, how are the processes executing, and what information can we gain from the parent process and that is given to the daughter processes, and pretty much just map out the whole topology of malware and that dynamic behavior. And additionally, if we develop a model, we want to make sure that it can perform and generalize well to unique malware instances and host environments. So it's not enough just to look at a single malware execution, but it's also note, can this malware be executed given different host environments where different benignware and the operating system is doing different things. So that's sort of where we want to generalize well, so that it's a very good discriminator as a future application. And one of the things that we considered for when it comes to features is, one thing we can do is we can look at the stack traces of event activity. And this is just to say whenever any process needs to make use of system resources, it ultimately needs to communicate with the kernel. And in doing so, there's a stack of Windows APIs that it needs to use in order to do so. And that goes all the way down to a high memory space where the kernel APIs are located. So we can look at all the dynamically linked libraries that a particular process uses, and then actually resolve exactly what APIs those are, And then with previous work, we were able to look at just the registry events, and we were able to obtain a pretty good F1 score based on registry events for previous implementation. There's different ways that we can represent these features. So these are Windows APIs, so they're kind of they're just text as is. But there's different ways that we can sort of represent that in feature space. One of the ways is called a bag of words, but there are alternatives where a bag of words just says if we have each node or process H1, H sub 2, or H sub 3, if that particular node uses an API, well, we're going to assign it a 1, and if it doesn't, we're going to assign it a 0. That way you can sort of map out which processes are using which APIs. But there's other alternatives, things like n-grams, which is say the unique combinations of APIs in sequence. That just tells us a little bit about more of the temporal sequence, because it sort of suggests when is this API used in a combination with this next API, and maybe that tells you a little bit more about its maliciousness. And of course, we have something called TF-IDF, which is term frequency inverse document frequency, which is a technique that actually looks at, rather than how common an API is used, what it actually also considers is it puts a greater weighting on APIs that are used less often, with the idea being that if there's a lot of overlap between Benignware and malware in terms of the APIs used, what you'd want to pay more attention to the rarely used APIs and consider those features more. So it's pretty much just a weighting on the frequency, hence the name. And one thing we wanted to look at more was with regards to the topology. So how do we model this topology? Well, one thing we can do is when we map processes to nodes, each node is given sort of, we can consider this sort of like a feature vector, which are these columns here. And ultimately what we're trying to do is we want to distinguish this node and that feature vector from V, for example, right? So we need a way to encode that relationship in some form of embedding space such that we want to maximize the similarity between the vectors, which are closely related. And we can do that with the dot product, right? So ideally with dot products, if their dot products are very similar, that kind of tells us that in the embedding space, they're very, if the dot products of the feature vectors are very close, that means in embedding space, they're very close together, and therefore they're more similar. So we want to create a model that can distinguish those malware from Benignware by forcing them into different parts of embedding space. And one thing way we can do that is we can map their topology through creation of a computation graph. And for those that aren't familiar, this is how graph neural networks work. So we can compute these node embeddings by looking at the elf hop and then building the computation graph. So for example, this node V here, for the small node in the top right, or sorry, the small topology in the top right, it's going to be influenced by the nodes around it, which would be the blue, the green, and the yellow. But if we wanted to consider further hops, you can actually look, okay, for green, what is its neighbors? Well, it's red itself and also orange. So we can sort of embed information about the closeness of the neighbors around it, and then build up that knowledge through combining those feature vectors. And the way that we can do that is through this equation right down here, where we have H sub U, H being the node feature vector. And then what we're doing here is, actually, let's just look at the sum, where it's the sum of U as an element of N. What that's saying is for a particular, for node V, look at all the neighbors, capital N of V, so all the set of neighbors of V, which are U. So take all of H sub U, which are all the neighbors, the feature vectors, and divide it by the cardinality of all the neighbors. So that's just saying combine all the neighbors of the nodes surrounding V, and then divide it by the number of neighbors so that so it averages it out. So it's an equal contribution based on the total number of neighbors. So that's just a normalization factor, and then multiply it by capital WL, which is a learnable weight feature matrix, and then multiply it by a non-linearity such as a sigmoid. So that's how you develop H sub V for that particular node. So again, that's just saying, look at all my neighbors around me, combine that information, transform it with a feature matrix that's learnable, and then introduce a non-linearity. So there's a message passing layer where you're passing the messages from the nearby nodes, and the aggregation is combining all that information. And one of the things we can do is, besides just divide by the cardinality, where it assumes all the nodes have an equal contribution based on their number, we can apply a multi-layer or perceptron transformation, again, which is just the capital W, so that's the same. but you can develop a weighted sum through A sub ij. So this is more complicated, and this was left out of the presentation, but this A here is sort of what's called an attention coefficient, and that just says, rather than considering all the contributions of the nodes equally, create another learnable facility that's able to learn the contributions of the nodes around me and assign them different weights, rather than just all of them equally, and all other things being the same with regards to the nonlinearity. So with regards to the data sets that we looked at, what we did was we looked at stack traces of event activity from different malware variants collected in our own virtualized environment, which is some of our previous work. So in this particular work today, we executed 239 malware samples, and we did so in the presence of 3 to 5 Benignware samples. That's just to say we created a unique host environment, a snapshot, executed malware with Benignware samples executed randomly from a collection of 300 from the apps from Windows category. The idea being is that we're getting a representative sample of different host environments when we have Benignware samples running. And then this little computation down here is just to say, for M given trials, what are the chances that a particular malware sample does or doesn't get drawn randomly, right? So again, more of that details in the paper. But as for a summary of sort of the methodology, one of the things we also did was consider different types of APIs. So for event type, we considered all the registry events. So those are APIs corresponding to the registry changes, the file system, to thread. And then we combine all of them in a single feature vector. And we looked at the different 1 gram, 2 grams, and 3 grams, again, which is just the combination of the APIs next to each other. And then what we did was we built up a topological graph for each malware execution into a computation graph of LHOPs. So what this sort of says is, on this little subfigure to the left here, this just says, hey, P sub 1 is influenced by itself and its parent, and P sub 1 at the very bottom here is influenced by itself and its parent. So it's only considering the one hop. But if we look to the subfigure to the right here, it actually looks up further in the chain, is able to combine more information about the nodes around it because of that additional hop. And this table at the right just shows that with all of our 239 malware, we computed some basic information about the topology based on how many nodes does a particular execution have, its node degree, its max node, min node. This just says how connected is the graph and what is the information contained around it. So as a quick summary of everything discussed so far, we took various malware, which are feature node representations, so we batched them. We created this formulation where we connected them together, and we computed these alphas, which is to say the importance of one node next to the other. And then we took these node feature embeddings, which is to say we transformed the feature into feature vectors, the APIs into feature vectors. We use that attention mechanism, which is actually, so the alphas we were just gathering the relationship between each nodes, but actually computing the importance. That's the use of attention here. And then inference is just to say, hey, so we built up this graph and we computed the LHOPs, and we did the message passing and the aggregation for a particular node that we don't know if it's malicious. What would its feature vector, or sorry, what would be its node embedding? Is it malicious or not? So we have that inference step. So as a result, just very quickly, everything can be nicely summarized actually in this graph. So what we have is these first 4 rows here just correspond to the computational graph neural network with different event types: file, registry, thread, and all. So in this case, loss is as the first column we want as low as possible, because that's learning loss. Sorry, validation loss. Accuracy, that would be macro accuracy, so we want as high as possible, and F1 score as high as possible, which considers both benign and malicious classes given the class imbalance. So one thing to note is that actually file system actually performed best. So when we're considering just the file system events, they had the most discriminatory power when it comes to identifying what's malicious and not. And that's just simply because you can look at, well, malware tends to create files, but also uses APIs where it's deleting itself very quickly, and that's very characteristic of malware. And even unigram events were the best discriminators, as opposed to bigram and trigram. So one of the reasons for this is, if we're considering rarely used APIs, when we're introducing more dimensionality and we're considering a lot of APIs next to other APIs, and they're not actually representative adequately in the data set, what happens is they tend to just add noise to the model and they don't perform very well. So at least with our implementation, just considering the APIs alone, whether or not they existed or not, based on their their inverse document frequency, what we noticed was Unigram did perform the best out of all models. And one other thing that we looked at was also difference in capacity of the model. So with that learnable weight matrix, capital W, you can actually add more neurons to it. So you're actually increasing the capacity of the model. So we actually looked at different sizes of the model, and we noticed that there was a good balance between 64 neurons in that hidden layer. And also the use of, and what we also noticed was the use of attention was very important. So just again, attention was learning that alpha, which is the importance of the nearby neighbors, and as opposed to GCN here, which is Graph's convolutional network, is just rather than learning those alphas and the importance of the nodes around us, just aggregating the feature vectors of the nodes around me and just dividing it by that cardinality. So that's what GCN is there. And then ANN is simple artificial neural network. That's to say, let's remove all the graph convolution. Let's not consider the nodes and just take the feature vectors of all the processes alone, malware and benignware, and then identify, is it malicious or not? So that's just to note that the use of attention has markable improvements over the GCN and ANN, and also it's over the ANN and the graph convolutional network. So as quick conclusion, we answer our questions. What features should we consider? Well, it turns out file system events with the Unigram corpus were the best discriminators of malicious and benign behavior. And how do we model topology? Well, graph neural networks are uniquely suited for this, and the use of attention outperforms simple ANN, or which also would follow from any machine learning algorithm. And it also shows improvements over the non-use of attention. And how well does the model perform? Well, based on our data set, which we find to be very robust, we did note 96.4% F1 score, and the macro accuracy was very high on what we consider a very representative custom data set. So with that, we thank everybody for tuning in. If you have any questions, please leave those in the comments section. Otherwise, you can send them to my email, my student email. And I thank everybody for watching.